Welcome to Math 2318. This is section 5.1. This is our new chapter on eigenvalues and eigenvectors. What does that mean to be an eigenvalue or an eigenvector? Well, if I have a matrix A and I multiply it by a vector V, if what happens when I do that, I get a scalar multiple back of that same vector, then that vector is called an eigenvector, and the particular scalar that does this is called the eigenvalue. Now, the eigenvalue can be a real number or a complex number. So, in question 1, they're asking us if this vector v, 1, 1, is it an eigenvector of matrix A? Well, let's see. What is A multiplied by V? So just do your regular matrix multiplication, and I end up with 3, 3. But 3, 3 is really just 3 multiplied by my original vector V. So yes, it is an eigenvector, and it has an eigenvalue of 3. All right, in question 2, same question. We have matrix A, we have a vector V. Is it true that V is an eigenvector, and what is the eigenvalue? So let's just grind through the multiplication of A times V, and I get 3 minus 3 minus 3, which is just 3 times my original vector. So 1 minus 1 minus 1 is an eigenvector of matrix A corresponding to the eigenvalue of 3. All right, so here in question 3, they're giving us a matrix A, and they're wanting us to know if lambda equals 4, is that an eigenvalue? And if it is, what is the corresponding eigenvector? Well, let's see. If lambda equals 4 is an eigenvalue, then when I form A minus 4 times the identity, then we're going to get a non-trivial solution. All right, so here's 4i. Do the subtraction. Now I'm going to do row operations to see what happens. I'm going to take row 1, divide through by minus 2, and then use it to make zeros under it. All right, I divided row 2 by minus 3, giving me 0, 1, 1, 0. I notice that's exactly the same as the last row, so I can multiply row 2 by minus 1 and add. And so what that tells me is x3 is free. x2 is minus x3 from this row. And from the top row, I get x1 equals x3. And so it is x3 multiplied by 1 minus 1 and 1. What that means is, yes, lambda equals 4 is an eigenvalue. It does have this particular eigenvector. In question 5, we are given matrix A. We are told lambda equals 11 is an eigenvalue. We want to find a basis for the eigenspace. All right, so I form A minus lambda I, where lambda is 11. All right, there it is. I now will solve the solution. When is that equal to 0? All right, so it's pretty easy. I can divide this row by minus 2 and then add. All right. And so what I get, x2 is free, and I get x1 is minus 2/3 x2. So I get x2 multiplied by this vector. Now, I can use this as a basis, or I can do a scalar multiple of it to get rid of the fraction. So I simply multiply both of these by 3. Either one can be a basis for the eigenspace. All right, in question 5, we are given matrix A. We're given its 3 eigenvalues, and so we want to find a basis for each eigenvector. All right, so using the 2, I form A minus 2I. All right, do the subtraction, get my matrix. I solve the equation for when is it equal to 0. I use the 1 to make 2 zeros under it. All right, at that time I can just divide this row 2 by 5. Make a 0 under it, so I completely get rid of row 3. So what does that tell me? That says that x3 from here is 0. x2 is free, x1 is 0. And so putting that together, that's x2 times 0, 1, 0. So for lambda equals 2, a basis is 0, 1, 0. So I repeat the process for 5, subtracting 5i, row reducing the matrix, again using this 1 to make some zeros under it. At that time I can divide this row by minus 3. And so what I see is it's really x3 multiplied by minus 1, 1, 1. So for lambda equals 5, this is our basis for the eigenspace. When it's 4, I repeat the same process again, subtracting, doing my row operations. I get that x3 times minus a half, 1 and 1, minus 1 and 1. And so to clear the fraction, multiply everything by 2. And so I get minus 1, minus 2, and 2 for the eigenvalue of 4. Find the eigenvalues of this particular matrix. Well, notice it is triangular. And by Theorem 1 in our textbook, the eigenvalues of a triangular matrix are the entries on the main diagonal. So I can just grab the entries right off the main diagonal, and the eigenvalues are 0, 7, and 6. Now in our last problem, we have vectors u and v, and they each have specific eigenvalues. U has minus 2, v has 3. We have our linear transformation. T maps R2 into R2, and it does it by multiplying by matrix A. All right, so let's see. What do I know? So 2 T of u is A times u, but since I have that u is an eigenvector, it's minus 2u. U is 4, 1. Where did I get that? Well, I just got that from the picture itself, 4, 1. V is 1, 3. All right, so what I get then is minus 2u. I find out what that is. And so T of u is this vector, which is minus 8, minus 2. T of v is A times v, but A times v is its eigenvalue multiplied by v. So 3 and 9. So where is that? That's over 3 and up by 9. Okay, so what I'm trying to figure out is which one of these pictures does it fit? Well, here's T of U, here's T of V, so yes, it will be C here. What about T of W? What's W? Well, W is the sum of the two vectors. So let's see, T of W is T of the sum, but T of a sum is T of U plus T of V. Well, I know what T of U is. I know what T of V is. I can add up the two vectors and I get minus 5 and 9 for T of W. And that matches the last little piece here for our picture of T of U, T of V, and T of W. And that concludes section 5.1 on eigenvectors and eigenvalues.